So it turns out that a special notation exists that uses the Greek letter capital sigma to express the sum of numbers or expressions. And so here, this is the capital sigma symbol, and this is the lower indice, and then this is the upper index. So the way that you would expand this is, notice that it says I equals 1 here, so you'd replace the integers between 1 and n for the I value there. So the way that you would rewrite this, let me erase these. So this is the same thing as A1 plus A2 plus A3 plus all the way to A sub n. And below here we have a table to help us figure out the sum formulas. The first sum formula tells us that if you sum 1 from I to n, that sum is just equal to n, because the way that you expand this is 1 plus 1 plus 1 plus dot 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 plus 1, and the number of times that this is happening is n times. So 1 times n is just n. Now, rule 2 says that if you multiply a constant times some function, you can basically pull the constant out, and those sums are equal. And then sum formula 3 says that if you have the sum of two things, you can separate them into two different summations. And example 4, I previously showed you. So if you have the sum of I equals 1 to n of I, that's equal to 1 plus 2 plus 3 plus 4 plus 5 plus dot 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 all the way up to n. And if you combine those, or if you want like a simplified formula for that, that summation happens to be equal to n times n plus 1 over 2. And then example 5 just says if you add up the squares of the first n integers, then that is equal to n times n plus 1 times 2n plus 1, all divided by 6. Now these formulas are going to help us in the following examples, so let's check those out. Example 3 says evaluate the following summations. So here, if I expanded this, this would be equal to 4 plus 4 plus 4 plus 4 plus 4, and that's going to end up equaling 20. Another way that I could have solved that summation is I equals 1 to 5 of 4. That is the same as 4. I'm basically pulling the 4 out, and then we're left with 1, and then we know that that's equal to 4 times, and then this summation based off rule number 1 up above from our table, we know that that is equal to 5, and so the sum is going to be 20. So those are both different ways that we could have found that. So if I were to expand summation b, this would be equal to 1 plus 2 plus 3 plus 4 plus 5 plus dot 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 all the way up to 129 plus 130. Now, that's a pain to calculate if you were to like do punch 1 plus 2 plus 3 plus 4 plus 5 plus dot 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 all the way up to 130 in your calculator. Fortunately, there is a formula that we could use from up above. So recall that from I equals 1 to n of I, that summation is equal to n times n plus 1 over 2. In this case, our n value is 130. So this summation is equal to 130 times 131 all over 2. And if you punch that into your calculator, you get 8,515. Okay, so part C, we want to take the summation of 3i squared minus I, starting from I equals 1 to I equals 40. I'm going to rewrite this. So rule number 3 in our table lets us to separate these. So that's going to equal the summation from I equals 1 to 40 of 3i squared, and then plus the summation from I equals 1 to 40 of negative I. And then from there, I can basically use rule number 2, the constant rule, And I can rewrite that now as 3 times the summation from I equals 1 to 40 of I squared minus the summation from I equals 1 to 40 of I. Now, both of these things now, we can use the formulas, formula number 4 and formula number 5. So this is now going to equal 3 times, and the I squared formula is, our n value is 40, so it's going to be 40 times 40 plus 1, which is 41, and then 2 times 40 plus 1, which would be 81 over 6, minus n times n plus 1 over 2, which in this case is our n value is 40, so it's going to be 40 times 41 over 2, like that. And then that's something we can just throw into our calculator, and you should get 65,600 as your final answer for that one. Example 4 says use rectangles to find the area under y equals x squared and above the x-axis from x equals 1 to x equals 0. So let's just quickly sketch a graph. Y equals x squared is a parabola, and it looks something like that. And let's say that's 1. So basically, we're creating a bunch of rectangles of equal width, and we're using and then adding those up in order to figure out. And notice that it doesn't say approximate the area, it just says find the area. So now let's talk about how we would find it exactly. And I'm going to create that same column table that I created before. So I've gone ahead and filled out the table like we showed in a previous example. Feel free to pause the video if you want to copy this down. But essentially, we've outlined the area of each of these rectangles. So if we were going to estimate or approximate this area here underneath the curve, then we would add up all of these values that we have here. One thing that I'd like to point out is, notice in this example we are using the left endpoints, and in the previous example we used the right endpoints, and it makes a slight difference in that the first rectangle is x sub 0, even though we're talking about rectangle 1. So that's a slight subtlety that you want to look out for in these examples. So if we are approximating the area, then the area is approximately equal to 0 plus 1 over n cubed plus 4 over n cubed plus ... plus the ith term, which would be I minus 1 squared over n cubed, plus ... plus, and then the last term, or the area of the last rectangle, would be n minus 1 squared over n cubed. And it's really nice now that we have learned the summation notations, because we can actually rewrite this entire thing as a summation using sigma notation. So this is equal to I equals 1 to n of I minus 1 squared over n cubed. Now, if you expand out I minus 1 times I minus 1, that becomes I squared minus 2I plus 1. So then we can rewrite that summation as this. And the n cubed, since it's not a function of I, we can actually take that out of the summation. So we could then rewrite that as this. And then we can separate that into 3 different summations. Okay, and now each of these things here, we can use the sum formula table to figure out each of these summations. So let's go ahead and do that. So we're still going to have that 1 over n cubed on the outside. The first summation we know is going to be equal to n times n plus 1 times 2n plus 1 all over 6. And that's just directly from the table. And then the second one, we're going to have minus 2, so that part doesn't change. And then times n plus 1 over 2. And then the last term is just going to be n from this third summation. And this term and that term will cancel out. And then let's see what we have after that. So if we distribute in the 1 over n cubed part, we will get n times n plus 1 times 2n plus 1 over 6n cubed minus n times n plus 1 over n cubed plus n over n cubed. And that's nice because a lot of the n's will cancel out, so that's going to turn into n plus 1 times 2n plus 1 over 6n squared minus n plus 1 over n squared plus 1 over n squared. And then if we find a common denominator and stuff, I'm gonna skip ahead a little bit, but if you do some algebra, the final thing that you end up with is 2n squared minus 3n plus 1 over 6n cubed. So basically we have now that the area underneath the curve is approximately equal to 2n squared minus 3n plus 1 over 6n cubed, where again n equals the number of rectangles. And so the notation that your textbook uses, so let's do some examples. So if n equals 10, then it uses S of 10 to represent the fact that you're summing up 10 rectangles. So the area is approximately S of 10, which is equal to, and then you just evaluate 2 times 10 squared minus 3 times 10 plus 1 over 6 times 10 cubed. And if you throw that into your calculator, it ends up being 0.285. And then if, let's say we wanted to, remember that the more rectangles you use, the more accurate your approximation is. So the area is approximately S of 100, and that's 2 times 100 squared minus 3 times 100 plus 1 over 6 times 100 cubed. And if you simplify that, that ends up being 0.328. So these are both just approximations though, and it turns out in order to get the exact area, what you could do is you could take the limit as n goes to infinity of the number of rectangles. So as n gets very, very large towards infinity, we'll get an exact answer. So the exact area is going to equal the limit as n goes to infinity of that formula we found, which was 2n squared minus 3n plus 1 over 6n squared. And it's been a while since we've found a limit like this, but remember what you want to do is you want to go through and divide each term by the highest power, which in this case is n squared. So that's going to equal the limit as n goes to infinity of 2 minus 3 over n plus 1 over n squared over 6. And let's see, this term and this term as n go to infinity are both going to 0. So that means that the area is equal to 2 minus 0 plus 0 over 6. And if you simplify that, that ends up being 1/3. So that is how you find the area in that example.